I can see the volume indicator moving, so I think something is working on this side at least.
So if you come over here, he can hear you.
Johannes, can you hear me?
I can hear you.
Okay, great. I think we can hear and see you now, so please proceed. If you don't mind, could you abbreviate it by 6 or 7 minutes? Sorry for the technical issues. Please go ahead when you're ready.
Well, right, you should never be the first person to do a remote talk, I can tell. Okay, so it's my pleasure to be here today and to talk to you about predicate EGRAPHS with symbolic conditional rewriting. This is joint work between Uppsala University and Ericsson. So the problem we're tackling is conditional rewrites, largely read. So we want to enable more conditional compiler optimizations in Erlang. Now these conditions may be contextual. They might arise from explicit program control flow. But we also want to handle conditions that arise from implicit control flow. We want to handle conditions that arise from provable properties that the compiler comes up with while it's running, or even runtime checkable properties. So this talk will introduce predicate EGRAPHS, will be fairly formal. It's about the definitions and the invariants and the different operations that are. This is work in progress, so in particular, we will not talk about an implementation. So to review very quickly, EGRAPHS, everybody knows what they are, or they wouldn't be here. We see an EGRAPH as fully defined by the triple of valid E-class IDs, the hash cons, and the find function from the union find structure. And given those three, you can get the E-class map. Now, a colored EGRAPH was invented in order to treat contextual rewrites. So where you have if statements and they have conditions and branches left and right and so on. So in general, you have a set of valid colors C equipped with a family of EGRAPHs, one for each color. There's a root color and there's a parent relation that goes from each color towards the root. So you can think of this as like the nesting of if statements, if you will. And what the interesting invariant of colored EGRAPHs is that in each color C, every E-class contains more nodes than it does in the parent. So the closer you get to the root, the fewer terms or the fewer nodes are equated. So we are generalizing colored EGRAPHs in this work. And we do that in order to handle conditions that do not arise from the static program structure or the syntax tree of the program. We generalize it in a way that each color instead is associated with a set of Boolean terms, the facts of that color. The relation between colors will approximate the implication order on these fact sets. So implication will form a pre-order. It might not be a tree in general. We want to admit edges to be inserted dynamically whenever you detect implications between such fact sets, whenever you can derive a fact closer to the root. And this might in turn create cycles in the implication order where you have equivalent colors. And such a cycle can be represented by a single canonical color. So a simple example is where we have an EGRAPH with 3 colors, root, less, and greater. At the root, the only fact that holds is true. And in the less EGRAPH, the facts are that true holds and A is less than or equal to 0. In the greater E-class, A is greater than or equal to 0. And then we introduce another EGRAPH where A is equal to 0. A fortiori, A is less than or equal to 0 and A is greater than or equal to 0. So this equal is below both less and greater. We have multiple parents in a sense for this node. So this is a well-known problem from inheritance in object-oriented languages and so on. So this kind of multiple thing. And this is exactly the kinds of structures that we want to be able to tackle with predicate EGRAPHs. So what does the formal definition look like? Well, a predicate EGRAPH is a set of valid colors. We have a family of EGRAPHs, one for each color as before. And instead of the parent relation, we have a pre-order on the colors, where root is the minimal element. It's furthest to the right in this pre-order. We have slightly more interesting invariants, perhaps. We have the same kind that each E-class contains more nodes in greater colors than in smaller ones. So the closer you get to the root, the finer the equivalence gets. And in order to come up with these fact sets, each EGRAPH has the truth E-class. which contains the true node. So the facts are just the elements, the terms that are represented by the truth E-class in every E-graph. We can always look up there and see what are the true things right now. We want to be able to modify this preorder as the program runs, and in order to modify it, we actually need a technical well-formedness condition that is below. It basically says that, well, if an E-class appears in two different E-graphs, well, then they both have a common parent from which this E-class originates. The basic operations on these things. Well, first of all, you have the standard operations. You have union, you have insert, you have match, which work on individual E-graphs. So they do exactly the same thing on the E-graph that you apply them to, but then afterwards you need to reestablish this invariant that the equivalence gets finer and finer towards the root. We could imagine that an implementation delays this for efficiency. But more interestingly, we have the kinds of dynamic operations that are particular to predicate E-graphs. We can add edges between colors, which updates the preorder. So if we add an edge from C1 to C2, well, that makes C1 greater than C2. C2 will be forced to be closer to the root than C1. This might seem innocent, but we remember that we need to reestablish the invariants. And to do that, we need to add all of the E-nodes of C2, E-classes of C2 to C1. We can do use iterated find calls and so on, and merge node sets. So this has been done in one way for colored E-graphs and in another one for at ICFP for these other E-graphs. And adding such an edge can close a cycle in. And there we can do some optimizations that I'll talk about later. We can, of course, we can add edges. We can also add colors. Add color takes a set of colors and creates a new color as an upper bound of these sets. So it will be a color that is greater than all of them. All of these colors, C1 to Cn, will be closer to the root than the new color. And also there we do some merging operations. So moving on to the example, we had this root, less, greater, and equal. And we can now decide to add a new color that is below both less and greater. Call it new, because why not? It appears here in the lattice. And the facts of new, well, as we said, the term equivalence gets coarser and coarser the further from the root we get. In less, we know that a less than equal to 0 is congruent to true. In greater, we know that a greater than equal to 0 is congruent to true. So in new, we need to have that both a less than equal 0 and a greater equal 0 be congruent to true. We can now look at the structure that we have and say we run some kind of mop-up reasoning pass. And we detect that the facts of equal actually contains all the facts of new. Well, equal also says that a is less than equal 0 and a is greater than equal 0. So we have detected this fact. This external algorithm can then say, okay, we add an edge from equal to new, like that. In that case, we may need to update things in equal, but since new is not really populated yet, nothing should happen in our simple example like this. You could add such edges automatically, because whenever you add a new node, it will be the least upper bound of its arguments. So any other nodes that have all of those as upper bounds will be further from the root than the new node. Conditional rewrites is sort of the raison d'etre of this stuff. If we have one of these rewrites rules, which we read from right to left as if x is less than or equal to y, then we can rewrite the term x greater than or equal to y to x equals y. If we have one of these conditional rewrite rules, we can apply it, and it only really has an effect in the new E-graph. And there it will derive that a is actually equal to 0. We detect the fact set inclusion in the opposite direction and add a second edge, which generates a loop. So now we have two colors, new and equal, that are equivalent in the pre-order. Their fact sets are equal, and we say that this is sort of the core property of an E-graph. What things are true in it? Well, if they're logically equivalent, and equivalence cycles can never be broken as long as you keep adding and adding and adding stuff, then we can actually optimize our representation and sort of only keep one of them. We can use a union find at top level to cache the pre-order equivalence, and we only need to keep one of the E-graphs, say the one that is furthest or was furthest down in the structure. We've seen conditional matching, but we have also defined symbolic matching. And why do we use that? Well, the happy path of a function, in particular in Erlang that we are looking at, may depend on multiple conditions. And we want to rewrite under the assumption that a bunch of these are true. But the problem is that, well, we might not have a particular color with a fact set that includes all of these conditions. For that reason, we define a symbolic matching operation, which is implemented using the standard conditional matching, which additionally returns a set of colors where all the required conditions are true. And then we can just use add color to create a new color with that property. To see how this is implemented, well, you can look at the extended abstract. So I hope I've caught up on time. And to conclude, we have defined predicate E-graphs. In addition to the usual operations that you have, they reflect the implication order of fact sets in pre-order colors. They admit external reasoning to add edges to color pre-order. We identify colors that have logically equivalent fact sets. And as far as matching goes, they admit this conditional matching, and it searches for the conditions in the facts of that color. We also have a notion of symbolic matching that is suitable for conditional rewrite rules with several conditions. This is fairly high-level work, which sort of looks at the structure of multiple E-graphs depending on facts and how you can manipulate this relationship between implications between fact sets and so on. So it would be very interesting to look at, okay, in terms of an implementation, we can look at versioned E-graphs as a template and see, can we extend versioned E-graphs to multiple parents? And that was my talk. Thank you very much. I'm very happy to take questions now online or in the Discord.
Okay. Thank you, Johannes, for bearing with us. Thank you, Johannes, for bearing with us through the technical difficulties. We're going to head to break now, but I encourage everyone to reach out via Discord in the Q&A section if you would like to ask the authors any questions. And authors, Johannes, please upload your extended abstract to the PLDI page so people can read it as you would suggested. Okay, we will resume here
come during the break.
10:40. Okay, see you all.